Hello students, in this class we are going to discuss about solid state lesson. We know that we have already discussed in the first year that matter means anything which has mass and which can occupy space, that can exist in three physical states. That is, first one is solid state, second one is liquid state, and third one is gaseous state. These three are the main three physical states that matter can exhibit. Okay, what are the main differences between these solid, liquid and gases? See here, in solids what happens? The constituent particles, these circles indicates what? They are the constituent particles. They may be atoms, they may be molecules, or they may be ions. It depends upon the nature of the compound. In ionic compounds, these were the ions. Okay, in molecular compounds, these are the molecules. So in solids what happens? The constituent particles, they are closely packed. The intermolecular distances, they are very short. They are closely packed and they are having fixed position. They cannot move their positions, but only the motion they can exhibit is they can vibrate about their mean positions. Okay, this is the main difference between solid, liquid and gas. In liquid what happens? There is a intermolecular forces of attraction, but they are not stronger as compared to solid. In gas what happens? In gaseous state, the constituent particles, they can freely move about. Okay, these are the main three differences between the solid state, the liquid state and the gaseous state. In this chapter we mainly focus on solid state. Okay, there are two forces that can determine the state of matter. So first one is intermolecular forces of attraction, and then thermal energy. Intermolecular forces of attraction, they tends to keep the molecules closer. Suppose if I take this first particle and the second particle, there is some force of attraction between these two particles. Okay, that is the intermolecular forces of attraction. What they try to do? They try to keep the molecules closer, whereas thermal energy, there is the energy of the constituent particles, that is a thermal energy, they tends to keep them apart. Okay, there are two opposing forces, they act at the same time. Okay, this is about the introductory part. Next we will move to the next one, that is general characteristics of solid state. This is very important one. What is the first one? Solids have definite shape and they are having definite mass and definite volume. Suppose if I take an example of a chalk piece, what it is? It is made up of small particles. So it is having a definite shape. Okay, and it is having some mass and it is having some volume. Okay, second one is intermolecular forces of attraction are stronger. In solids what happens? Between the two particles there is a strong force, that is intermolecular forces of attraction. Okay, then third one is intermolecular distances are shorter. Between the any two particles, what happens? The intermolecular distances, they are almost closely packed, but some distance is there, so that intermolecular distances are shorter. Okay, then the fourth one, very important one, that is solids are incompressible and they are rigid. What do you mean by compressibility? If we take an example, sponge, ನಾವೇನು ಮಾಡ್ಬೋದು? ಸ್ಪಂಜ್ನ we can compress the sponge, but solids we cannot compress. The chair, the table, those are the examples for solids. We cannot compress the solids and they are rigid in nature, means they are having fixed position. Okay, then this is a very important for the examination point of, that is a classification of solids. They are mainly classified into two types. First one is crystalline solids and then second one is amorphous solids. What are the main differences? First one is solids in which constituent particles are arranged in a regular 3D arrangement throughout. Throughout the solid what happens? The constituent particles, they are arranged in regular 3D. Okay, in 3-dimensional they are arranged, but in amorphous solids what happens, they are arranged in a irregular pattern. They are arranged in irregular pattern. Suppose in crystalline solids what happens, the constituent particles, they are in 3D. 3D means just below the one. This is an example for crystalline solids where the constituent particles, they are arranged in 3-dimensional. Okay, throughout. But in amorphous what happens, that is irregular. Only up to some extent they can arrange. This is example for amorphous solids and it is an example for crystalline solids. Then second one is they have sharp melting points. ಏನು ಮಾಡ್ತೈತಿ, crystalline solids they are having sharp melting point, but amorphous solids they are melt gradually over a temperature range. Example ಏನ್ರಿ, amorphous solids example is ಪ್ಲಾಸ್ಟಿಕ್. ಪ್ಲಾಸ್ಟಿಕ್ ಏನು ಮಾಡ್ತೈತಿ, ನಾವು ಹೀಟ್ ಮಾಡಿದ ತಕ್ಷಣ ಎಟ್ ಅ ಟೈಮು ಎಲ್ಲ ಬರ್ನ್ ಆಗಂಗಿಲ್ಲ. ಏನಾಗ್ತೈತಿ, ಓವರ್ ಇಟ್ ವಿಲ್ ಟೇಕ್ ಅ ಫ್ರ್ಯಾಕ್ಷನ್ ಆಫ್ ಸೆಕೆಂಡ್ಸ್ ಟು ಮೆಲ್ಟ್. ಸೊ amorphous solids they melt gradually over a temperature range, but the crystalline solids they have sharp melting point. All the crystals they will melt at a same time. Okay, then third difference is they are anisotropic in nature, whereas amorphous solids they are isotropic in nature. Then the question arises, what do you mean by anisotropy and what do you mean by isotropic? So this is a model to explain about this. Okay, anisotropy in crystals. See here what happens, this represent the constituent particles 1 2 3 4 5. They represent constituent particles. Suppose if we take these big circles as a anions and these small circles as a cations, here see the arrangement from C to D. What is the arrangement? First is a anion, then cation, then anion, cation, anion, cation. Like that it is arranged from C to D. But from A to B what happens, only the cation arrangement is there. So we call this one as anisotropic. Anisotropic means what? The different number and different type of particles. See, from C to D there are two different type of particles involved, but from A to B only one type of particles are involved. Such type of crystals is called as anisotropic crystals. Examples is physical properties like refractive index and conductance. Okay, then the fourth important difference is they are true solids. Crystalline solids they are called as true solids, whereas amorphous solids they are called as pseudo solids. Why we call them as pseudo solids, or sometimes we call them as super cooled liquids? Because they have a property to flow like a liquids. That's why we call amorphous solids as pseudo solids or super cooled liquids. Okay, then the fifth one, the constituent particles they are having long range order. Like this, the crystalline solids, in crystalline solids the constituent particles they are having long range order, while in amorphous solids the constituent particles they are having a short range order. They are having long range order and these are having short range order. Then sixth important difference is they are having a definite enthalpy of fusion, whereas amorphous solids they do not have definite enthalpy of fusion. Then the question arises, what do you mean by enthalpy of fusion? What happens if we heat the solid? If we heat the solid, it will convert into liquid, and if we heat the liquid, it is converted into gaseous state. Okay, this process is called as fusion. Conversion of solid into liquid is called as fusion, whereas conversion of liquid to gas is called as vaporization. Conversion of solid to liquid is called as fusion. Conversion of liquid to gaseous state is called as vaporization. Here the sixth difference is they are having definite enthalpy of fusion. Suppose if we heat crystalline solids, they are completely converted into liquid, but here they do not have definite enthalpy of fusion. Some particles remains as a solids in amorphous solids. Okay, the last one is examples. Examples for crystalline solids is sodium chloride, quartz, diamond, and etc. In amorphous solids, example is glass, rubber, and plastic. Okay. Then this is a very important crystal lattice, or we call them as unit cells or space lattice. Both are same. Crystal lattice is nothing but the space lattice. Then the question comes, what is crystal lattice? Okay, crystal lattice means it is a 3D arrangement of lattice points. Here the red circles now we call them as lattice point. What they represent? They represent the position of the constituent particles. Okay, these red circles, what they indicate? They are the lattice point and they represent particles, constituent particles. Okay. Then what do you mean by lattice points? The constituent particles which generate the unit cell. See here, the blue circle is called as this structure is called as unit cell, where the constituent particles are, we call them as lattice points. They are forming this unit cell. Okay. Then the definition of unit cell is the smallest part of the complete crystal lattice, which when repeated again and again in all possible directions result in the formation of crystal lattice. See here, it is, this whole thing is called as lattice, but this only one thing, this one is a unit cell. They are repeated. See, they are repeated again and again to form a crystal lattice. Okay. Then question comes, the interfacial angle. What do you mean by interfacial angle? See here, this alpha, beta, gamma, we call them as interfacial angles, and this bond length A, B and C, we call them as bond length, or we call them as edge length. So A and B and C, this is a cubic unit cell. This is a cubic unit cell where A, B and C, they are the bond lengths, and alpha, beta, gamma, they are the bond angles, or sometimes we call them as interfacial angle. Whatever the size of the unit cell, the interfacial angles remains same. This is what the law of constancy of interfacial angle. What it states, the interfacial angle for a particular crystal lattice remains constant no matter what the size of unit cell. Size small irli, big irli enagtೈತಿ, interfacial angle difference iralla. The interfacial angles are same in case of small unit cell or big unit cell. Okay. Alpha is the angle which is present between B and C. Opposite to the bond length A, alpha is present, and opposite to the bond length B, beta is present, and opposite to the bond length C, gamma is present. Okay. Then classification of unit cell. First one is simple cubic unit cell, and then second one is centered cubic unit cell. We classified this unit cell into two parts. First one is simple cubic unit cell, and then second one is centered cubic unit cell. So what do you mean by simple cubic unit cell? This is an example for simple cubic unit cell. Okay, the constituent particles, they are present only at the corners. See here, the purple color balls, they are the constituent particles. They are present only at the corners. If they are present only at the corners, we call them as simple cubic unit cell. Then second one is centered cubic unit cell. ಅದರಲ್ಲಿ ಮೇನ್ 3 ಪಾರ್ಟ್ಸ್ ಬರ್ತಾವ, 3 ಟೈಪ್ಸ್ ಬರ್ತಾವ. ಅಲ್ಲಿ ಇಲ್ಲೇನಾಗ್ತೈತಿ, ದ ಕಾನ್ಸ್ಟಿಟ್ಯೂಯೆಂಟ್ ಪಾರ್ಟಿಕಲ್ಸ್ ದೇ ಆರ್ ಪ್ರೆಸೆಂಟ್ ನಾಟ್ ಓನ್ಲಿ ಎಟ್ ಕಾರ್ನರ್ಸ್ ಬಟ್ ಆಲ್ಸೋ ಎಟ್ some other specific positions. They are present at the corners. See, in all type of unit cells, the constituent particles, they are present in corners. ಹೌದಾ, ಇಲ್ಲಿ they are present in corners. Second type, they are present in corners. Here also corners, here also corners. But what is the main difference? In a centered cubic unit cell, they are present at some other positions also. In simple cubic unit cell, what happens? They are present only at the corners, but here they are present with at some other positions. Okay, the name itself indicates body centered cubic unit cell. At the center of the body, at the center of the body, one lattice point is present, 8 present at the corners and 1 present at the center of the body. Then the third one, face centered cubic unit cell. Here what happens, the constituent particles, they are present at corners. These yellow dots indicates what, they are the present at the corners. These red dots indicates they are present at the face. Suppose if I take a box, what happens, there are 6 faces, no, top one, bottom one, front, back and left and right. So there are 6 faces. At each face one constituent particle is present. At each face one constituent particle is present. Suppose if I take this is as a box, this is what, unit cell. Here what happens, this is a front face and it is a back face. This is top and then bottom, left and right. Totally how many faces? 6 faces. So 6 constituent particles. See, 1, 2, 3, 4, 5, 6. 6 are present in the face centered cubic unit cell. In addition to 8 at the corners, 6 are present at the center of each face. So total there are 14 lattice points. Here total there are 9 lattice points. Then the last one is end centered cubic unit cell. ಇಲ್ಲಿ ಏನಾಗ್ತೈತಿ, the lattice points they are present at corners. ಕಾರ್ನರ್ಸ್ ಅಲ್ಲೂ ಪ್ರೆಸೆಂಟ್ ಇರ್ತಾವ, ಪ್ಲಸ್ ಎಲ್ಲಿ ಪ್ರೆಸೆಂಟ್ ಇರ್ತಾವ, ಬಿಟ್ವೀನ್ ದ ಅಪೋಸಿಟ್ ಫೇಸಸ್, ಎನಿ ಟು ಅಪೋಸಿಟ್ ಫೇಸಸ್. ಸಪೋಸ್ ಇಲ್ಲಿ ಟಾಪಲ್ಲಿ ಇದ್ದರೆ ಒಂದು ಬಾಟಮಲ್ಲಿ ಇರ್ತೈತಿ, ಒಂದು ಲೆಫ್ಟ್ ಇದ್ದರೆ ಒಂದು ರೈಟ್ ಇರ್ತೈತಿ. ಲೈಕ್ ದಟ್ ಬಿಟ್ವೀನ್ ಎನಿ ಟು ಅಪೋಸಿಟ್ ಫೇಸಸ್ 2 lattice points are present. So total there are 8 lattice points which are present in end centered cubic unit cell. Okay, next one, these are the types of crystal lattice. Okay, in cubic what happens, where edge length A is equals to B is equals to C. We already saw that in interfacial angle, where A equals to B equals to C and alpha, beta, gamma which is equals to 90 degree. And then examples are KCl and zinc sulfide, potassium chloride and zinc sulfide. So these are the important types of crystal lattice. Like this, if we see triclinic, where A is not equals to B is not equals to C. This means what? All the bond lengths, they are not equal with one another. Okay, all are different. And alpha is not equals to beta is not equals to gamma is not equals to 90 degree. ಮೂರನ್ನು ಏನಿರ್ತಾವ, ಅಲ್ಫಾನು 90 degree ಈಕ್ವಲ್ ಇರಲ್ಲ, ಬೀಟಾ is not equals to 90 degree, gamma is not equals to 90 degree. Example is potassium dichromate and H3BO3. Okay. The most important 2 points is here. Cubic crystal is the most symmetric crystal lattice. Why we call this cubic crystal as the most symmetric? Because see here, where edge length A is equals to B is equals to C. Edge length nu same idava and axial angles alpha equals to beta equals to gamma and all 3 equals to 90 degree. So cubic crystal is the most symmetric crystal lattice. And see the last one, triclinic system. It is the most asymmetric crystal lattice because all the 3 edge lengths they are not equal and all the 3 interfacial angles they are not equal. So we call this triclinic system is a most asymmetric crystal lattice. Then this is a very very important. Okay, position of the atom, then number of unit cells with which shade and contribution towards one unit cell. It means what? See here, okay, this is a lattice. Suppose if we take this lattice point, it is common to this unit cell and here this is a shaded one and this is a unshaded one. This is common to this unit cell. Okay, so there are so many unit cell which we cannot express because which is in 3-dimensional, so we cannot represent it on the board. Okay, this lattice point which is common to this unit cell, the backward, the top one, the left one, like that it is common to so many unit cells. Like that in the body centered cubic unit cell only one is present, no, 8 are present at the corners, only one is present at the center of the body. So which is only which can number of unit cell with which it can shade is only 1. So one contribution is 1. In face centered what happens, one constituent particle which is common for 2 unit cells, so the sharing is 1/2. Okay, then at the edge center it is contribution is 1/4. Then the calculation of total number of lattice points per unit cell, it is very very important. Okay, 2 ಮಾರ್ಕ್ಸ್ಗೆ ಕ್ವಶನ್ ಬರುತ್ತೆ. 3 ಅಲ್ಲಿ ದಿಸ್ 4 ಅಲ್ಲಿ ಒಂದು 2 ಮಾರ್ಕ್ ಕ್ವಶನ್ಸ್ ಕಂಪಲ್ಸರಿ ಬರ್ತೈತಿ. ಹೌ ಟು ಕ್ಯಾಲ್ಕುಲೇಟ್ ದ ಟೋಟಲ್ ನಂಬರ್ ಆಫ್ ಲ್ಯಾಟಿಸ್ ಪಾಯಿಂಟ್ಸ್. ಸೊ ಹಿಯರ್ ಸಿ z equals to, this is a formula. This is a formula. Z equals to total lattice points into contribution. Now already we saw that the contribution is here, no? The contribution is here. The contribution is here. So for the calculation of this total number of lattice points, we must have the knowledge of that one. So the z equals to total lattice points into contribution. This is what the simple cubic unit cell. Here what happens? The total lattice points count 1, 2, 3, 4, 5, 6, 7, 8. So there are total 8 lattice points. So I write it at A8 and into contribution is 1 by 8th. So contribution is 1 by 8th. 8 ones are 8 ones are. So we cancelled out. So we are going to end up with 1. Okay. Then if we consider body centered cubic unit cell, 8 lattice points, they are present at the corners. So it is 8 into contribution is 1 by 8 plus, see here, 1 is present at the center of the body. So add plus 1, we are end up with 2. There are 2 total number of lattice points per 1 unit cell. Then see here, it is a face centered cubic unit cell. The first thing is common, 8 are present at the corners and we are going to divide it by 8 plus 6, they are present at each faces. Okay, so 6 into the contribution is 1 by 2. 8 into 1 by 8 is 1 plus 6 into 1 by 2 is 3. Then 4, total is 4. So there are total 4 atoms which are present in a 1 unit cell. Then last one is end centered cubic unit cell, where the contribution for the corners is same, that is 8 into 1 by 8 plus 2 are present at the opposite faces, no? So 2 into contribution is 1 by 2, total 2 atoms present per unit cell. Then the important one, this is a packing efficiency. What do you mean by packing efficiency? If see here, in a box we are taking, in a box what we are taking so many colorful balls, isn't it? So in a box we are taking so many colorful balls, we are placing them on one another. See, even we are placing it, there are some gap between the balls, no? Some gap between balls. So we call that as void. VOID. Void is nothing but the empty space. Void is nothing but the empty space. So even if we fill the ball, we fill the box with the balls, there is some empty space between the balls, we call that one as void. Then packing efficiency means what? It is a percentage of total space occupied by the particles. Suppose if it is 100%, box volume is 100%, 100% ಅಲ್ಲಿ ಬಾಲ್ಸ್ ಎಷ್ಟು ವಾಲ್ಯೂಮ್ ಅಕ್ಯುಪೈಡ್ ಮಾಡಿದಾವೆ ಅದಕ್ಕೆ ಏನಂತೀವಿ ನಾವು ಪ್ಯಾಕಿಂಗ್ ಎಫಿಷಿಯನ್ಸಿ ಅಂತೀವಿ. ಪ್ಯಾಕಿಂಗ್ ಫ್ರ್ಯಾಕ್ಷನ್ ಮೀನ್ಸ್ ಇಟ್ ಈಸ್ ಅ ಸೇಮ್, ಬಟ್ ಇಲ್ಲಿ ನಾವು 100ಗೆ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ, ಇಲ್ಲಿ ಫಾರ್ 1 ಆಟಮ್ ಕ್ಯಾಲ್ಕುಲೇಟ್ ಮಾಡ್ತೀವಿ. ಸೊ it is a very important formula. Packing fraction, it is a volume occupied by the particles. ಎಷ್ಟು ವಾಲ್ಯೂಮ್ನ these particles balls occupy ಮಾಡಿದಾವೆ divided by volume of the unit cell. Volume of this box is nothing but the volume of unit cell, and volume occupied by the particles is nothing but this volume occupied by the balls. Then packing efficiency is the same formula into 100 is nothing, it is a packing efficiency. Okay, then packing efficiency, how to calculate the packing efficiency in simple cubic lattice. In simple cubic lattice, see here, in simple cubic unit cell, the constituent particles, they are present at the corners only they are present at the corners. If I take these two particles, so these are the spherical atoms. Okay, this is a distance r. Let A be the edge length of the unit cell. A be the edge length of the unit cell. We know that in a cubic unit cell, all the lengths are same. Suppose if it is A, all the edge length is a A. Okay, this is a A. Here see what happens. A equals to R plus R. This is one R, this is another R. That is A equals to 2R. Suppose A be the edge length of the unit length, R be the radius of each particle. Then we have A equals to 2R. We have A equals to 2R. The volume of the unit cell. This is a formula. Volume of unit cell, how we calculate? We calculate it into height into length into breadth. Okay, that is A into A into A. That is A cube. That is A equals to 2R. So A cube means I substitute 2R in place of A. 2R whole cube. That is 2 into 2 into 2, 8. R into R into R, R cube. We know that in simple cubic unit cell, the total number of particles present is 1. So the number of particles per unit cell is 1. Therefore, the volume occupied by the particles, it is a mathematical formula. Volume occupied by the particles, that is 4 by 3 pi r cube, because this is a spherical atom, no? So for spherical atom, the volume occupied by the particles is 4 by 3 pi r cube. Again, this is a formula. Packing efficiency equals to volume of one atom divided by volume of cubic unit cell into 100. We know that the volume of one atom is 4 by 3 pi r cube divided by this volume of unit cell is 8 r cube into 100. If we continue this calculation, we are end up with 52.4% as a packing efficiency. Okay, this is in case of simple cubic unit cell. This is very important for 5 mark. Okay, then second one is packing efficiency in a body centered cubic unit cell. Here what happens? One constituent particle that is present in the center of the unit cell. So if I join all these 3 points and all the 3 circles, what happens? Okay, if I join these 3 circles, this distance is called as R, and this distance we call it as R. This distance again R and R. So total how many R? There are 4 R. So 3A square. This is 1A, another A and third A. ಈ ಪಾಯಿಂಟಿಂದ ಈ ಪಾಯಿಂಟ್ ರೀಚ್ ಆಗೋವರೆಗೂ ಎಷ್ಟು ಎ ಇದ್ದಾವೆ? ನಂಬರ್ ಆಫ್ ಎಸ್ ಆರ್ 3. So 3A square equals to 4R whole square. Here there is a calculation. So we are end up with R and A relation, that is R equals to root 3A divided by 4. Here also the volume of unit cell is A cube. The volume of unit cell is same in all cases, and number of particles per unit cell is 2. Number of particles per unit cell is 2, because in body center the number of particles is 2. Again the same formula, and 2 into 4 by 3 pi r cube. On doing this calculation, we are end up with the packing efficiency 68%. The last one is packing efficiency in face centered cubic unit cell. What this means? HCP and CCP. HCP stands for hexagonal cubic packing. HCP for hexagonal cubic packing and CCP for cubic close packing. Okay, all these 3 are same. In this case what happens? A be the edge length, this is same for all, and for face centered cubic unit cell, A equals to 2 root 2 R. Okay, by Pythagoras theorem we are calculating this A, and volume of unit cell is A cube. A cube means 2 root 2 R whole cube, and doing these calculations we are end up with the packing efficiency 74%. Okay, thank you. We will continue this lesson in the next session. Thank you.